Planck until 2007. He's still there, but he retired as director in 2007. Since then, he's been an adjunct professor at Lamont, which is why we had the opportunity to convince him to come down and spend some time with us as a Tuve fellow. So I'll stop there and say, Al, it's a great pleasure having you here, and he'll present a talk on a new look at the composition, size, and evolution of the depleted mantle.
Working? Is it working? Thank you. Well, thanks, Rick, for inviting me here, bringing me back to my old stomping ground. It really feels good to be here. And it's wonderful to see that Carnegie, both DTM and the Geophysical Lab are thriving. And it really, I appreciate this invitation very, very much. But you shouldn't exaggerate quite so much when you're talking about me, Rick. It embarrasses me. Sorry. Yeah. And what I want to do is talk a little bit about this big subject of crust-mantle differentiation. And I put on a subtitle here, How to Be Isotopically Incorrect. Oops, this is getting kind of weak here. It was working much better before. and just try to give you an impression, of how sophisticated this whole thing was. And in a previous installation of this talk, I threatened I would spend the next 20 minutes going through these equations. But I have to admit to you, I have never done it myself, so, this is not the only page in this paper, okay? So a lot of heavy artillery. So let's go back to that simple system. Highly simplified Earth, depleted mantle, producing the continental crust and leaving some primitive reservoir. Okay, now people have done this in a simpler way. I won't go into the details of that with somewhat less mathematical artillery than Jacobsen and Wasserberg did. And they tried to figure out the actual chemical composition of that depleted reservoir. And here are two popular recent efforts, highly quoted papers by Ria Workman and Stan Hart in 2005 and by Salters and Stracke in 2004. Here's a slight variation of that Workman and Hart paper. Never pay attention. Basically, they're very similar. And I just want you to notice here that the depletion, and a good one I think to look at is the abundance of thorium and uranium relative to the primitive mantle, which by definition is 1.0, okay? So they have only about between 10 and 20% of the thorium and uranium abundance of the primitive mantle. So they don't, for example, have 10 and 20% of the thorium and uranium abundance of the primitive mantle. So they don't, for example, gone, okay? And so these are the papers that are used by geophysicists and geochemists now when they want to model what the depleted mantle does. Okay, and I didn't go into the detail, so I just showed you the result that this is highly depleted, this residual mantle. But it also, another result is that it constitutes only 25 to about 30% of the total mantle. And this is quite important because it confirms an old prejudice that we all had, namely that the upper mantle above the 660 kilometer seismic disk, I see Selwyn Sachs is nodding, above the 660 kilometers discontinuity is that the reservoir which has given rise has produced the continental crust, and what's beneath that is less depleted or maybe still completely primitive. And this was a very popular model to which I subscribed to myself for some years with some trepidations, but nevertheless. And just to make life a little easier, a fellow by the name of Jeff Davies from ANU simplified this whole business, so you didn't have to go to these complicated Jacobsen and Wasserberg equations, pages and pages of equations, but boiled this whole thing down to a simple mass balance, a set of simple mass balance equations. Namely, these are the mass fractions of these three reservoirs. These are the concentrations of some elements such as neodymium in these three reservoirs. And if these reservoirs have some other characteristic like an isotopic composition expressed here by epsilon, which I showed in one of my first slides, it follows this equation. And this is something that you can solve very easily with paper and pencil on the back of an envelope, more or less. Anyway, so the solution to these equations are these. Okay, this is the size of that residual reservoir expressed in terms of the fraction of the continental crust, the concentration of that element in the continental crust, the isotopic composition in the residual reservoir and in the continental crust. And this is the primitive mantle concentration. These are the isotopic composition in the primitive mantle, which we think we know from meteorites. And this is the residual mantle isotopic composition, which we think we know from sampling basalts, which are derived from that, which are supposed to show us the same isotopic composition as that mantle reservoir from which the basalts are extracted. Once we have that, we plug that back in the equation, and we actually get the concentrations of that element in that residual reservoir, okay? So that's all the equations I'm going to use. And Jeff Davies wrote these down back in 1981. I think people paid very little attention to this. I don't know why not, probably because it's too simple. If you do that, so you can get exactly the same answer that Jacobsen and Wasserberg did with their very elaborate artillery. The only unknown or the least well-known parameter in this system is actually the composition of the continental crust. And so I have formulated this here in terms of the continental crust, where we don't know the epsilon value, the isotopic composition of the continental crust. We know the upper continental crust pretty well. It's about around -10, -11, -12, something like that. We know this from shales and sediments in general, which sample the upper continental crust pretty well, but we don't know the lower continental crust very well. So Archean sediments, for example, would be that. Well, the bulk crust certainly doesn't have this composition, but it might, for example, have this kind of composition. So we don't know. But you can see that if you take the average composition of mid-ocean ridge basalts, as we know today, which has an epsilon value of about 8.5, and we take 15 here as a bulk continental crust, we get something like a mass fraction of the depleted mantle of 25%. If we go to the -20, we get 30%. Okay, so the point is that there's some uncertainty there, but all the answers are that the mass fraction of the depleted mantle is small. It's not, it doesn't incorporate the lower mantle. It's essentially confined to the upper mantle. Okay, so that you can simply get that by the simple mass balance. Okay, but now the geophysicists used to sort of like this because of that mantle discontinuity, 660 kilometers up here. So this was the kind of model. So everything we do in plate tectonics and so forth was supposed to happen up here in the upper mantle, and that geochemical model fit this very well. But then the geophysicists invented seismic tomography and things like that, and they noticed that maybe it's not that, that's not actually how the mantle works, but you have subduction that goes down deep. Now, if you have a big slab that goes down in the lower mantle, it'll start to mix this thing up. You know, you cannot preserve that chemical and isotopic identity of these two reservoirs if you got big slabs of stuff going through there. And also, if you have things like mantle plumes coming up from below, and so this artist's rendering of the mantle, Garnero has the, the prettiest pictures of that. You'd be hard put to find a discontinuity at 660 kilometers in the structure and dynamics of the Earth mantle today, looked from the point of view of the geophysicist. And so we have an increasing discrepancy of the view that we inherited from the isotope geochemistry with that which we think we actually know from geophysics today. There is more, okay? There is now, in the last 15 years or so, this large low shear velocity provinces known universally now as LLSVP, okay, large low shear velocity provinces. They really dominate the lower mantle, and the latest paper I've seen on this is that they occupy something like 9% of the total mantle are these things of low velocity in the lower mantle. Earlier papers said they're only 3 or 4%. Now maybe the upper bound is a little difficult to determine, so it might be a lot more than 3 or 4%, namely their best estimate is 9%. Doesn't matter. It's a sizable amount. It's actually much less than continental crust, which is only about 0.5% of the mass of the total mantle. Okay. And then, of course, we have mantle plumes, always a controversial subject, of course. But the latest paper by French and Romanovitz show these mantle plumes coming right from the core mantle boundary, going up to the surface, and these things are big. They have a diameter of on the order of 600 kilometers. So if you have subducted slabs going down, and mantle plumes rising from above. This will mix up the mantle, and the layering will be destroyed within a relatively short time of relative to Earth history. Okay, so what's wrong with the isotope story? Okay, and the question I like to ask is this, what I call the critical question. Is the depletion, namely the increase, when the geochemist says depletion, what he really means an increase in samarium-neodymium ratio. You'll have to forgive us for this one. Is that depletion of the depleted mantle, which is the MORB source, caused only by extraction of the continental crust, or maybe there's something else going on which we haven't considered? And if that's the case, if it's not just the continental crust that's doing the trick, then the whole calculation is wrong, of course, and the whole basic, very simple model is wrong. Okay. So we can examine the data set a little bit from that point of view and see what the relationship of the isotopic and chemical composition of the continental crust to that, what we see internally in the data from the mid-ocean ridge basalts. And we don't see any actual encouraging signs that the continental crust plays any big role in this. For example, here, if we plot the isotopic composition of neodymium in mid-ocean ridge basalts, and these are averages of actual mid-ocean ridge segments in a compilation by Gale and, oops, I forgot to write this on here, of Gale and Langmuir, published just a few years ago. So this is globally representative, and there are a few outliers here, but by and large, they form actually a pretty strong correlation with, you know, an apparent age which probably has no real meaning, but nevertheless, it's not a very old thing here. And you plot the average continental crust on here, which might be somewhere between -10 and -15, a samarium-neodymium ratio of something like this. You see no indication that those two kind of things are related to one another. So it's not clear that the extraction or the feeding back of continental crust has all that much to do with the actual isotopic composition of that mid-ocean ridge basalt source reservoir. You can look at other isotopic systems and say, well, maybe neodymium is no good. Maybe we should look at lead. I'm not going to get into lead except for this one slide because, you know, the isotope geochemist says nobody understands lead isotopes except you and I'm not so sure about you. And so, but I will show this diagram. Just amongst us here, you know, xenon isotopes are worse, but I won't show xenon isotopes at all. You plot mid-ocean ridge basalts and ocean island basalts on this lead isotope diagram. Never mind what all that means. And you plot estimates of the bulk upper and lower and average continental crust. And these crustal rocks form a trend which has nothing to do with what we see in the oceanic basalt. So again, it's hard to argue from this that isotopically this stuff is produced by extracting continental crust from the mantle. So there's something fishy here. Okay, so I would just conclude in a preliminary way that the radiogenic isotopes are poor tracers of crust extraction. And the reason for that, I would claim, is that the parent-daughter ratios, samarium, neodymium, rubidium, strontium, there's more lutetium, hafnium, uranium, lead, thorium. These are all the long-lived isotope systems that we use. I left out rhenium, osmium. They are fractionated by all kinds of magmatic processes, not just continent extraction, okay? In all these models, we have assumed that the depleted reservoir, what we sample there, is produced only by continent extraction. If that's not true, these models are dead. So I would just, in parentheses, add to that the dominant magmatic process on Earth is actually formation of oceanic crust, not continental crust. And oceanic crust is subducted back into the mantle, okay? So this should have given us pause to worry about this whole kind of model. Do we have a better tracer than isotopes? Now I'm betraying the isotope geochemist. and I show you an ugly trace element plot. This is what we call a spidergrams. Never mind, it's a stupid expression. And I fought it for something like 20 years of my career, but I've given up. I'm now calling it spidergrams too. So what, if you, the discerning eye can notice a couple of prominent features here. And that is all the continental rocks, and I have only two classes here, those light green ones, namely average continental crust, and gloss is the global subducted sediment Terry Planck's. She sampled all sediment things in front of subducting arcs and for, around the world. So her gloss is the sediments that are being globally subducted. And they look very much on this diagram like just average continental crust. And what they have is they have this big negative kink here in the niobium anomaly relative to thorium and uranium, potassium, barium, and so forth. They also have a positive kink in the lead isotopes, but I won't talk about that today. I will just concentrate on the niobium. All the rocks derived from oceanic environments. Oh, and I should add that if you, and I had neglected to plot subduction type volcanics, island arc basalts, they would also show the same kind of thing. Island arcs ultimately lead to the formation of continental crust, and they share this feature of negative niobium anomalies. For whatever reason, there are some good petrological ideas, but in detail, we don't actually even know why this is the case. But it's an observation which holds essentially universally true. All the oceanic rocks have what I would call complementary positive anomalies. Here, mid-ocean ridge basalts. Here's a Hawaiian tholite from Mauna Loa. Here's some other ocean island basalts, and they all have these positive niobium anomalies. So now these are just kinks in some spidergram. We want to have something. We want to use this tool in a quantitative way. We can't use this kind of diagram quantitatively, or at least maybe you can, but I can't. So we have to recast that in some more sensible fashion for that purpose. And way back early in my career, I made a first attempt with relatively lousy data. There's only a few dozen points here. At that time in the 80s, in Mainz, we were the only laboratory that could actually analyze low niobium concentrations in depleted mid-ocean ridge basalts, because at that time there was no ICP-MS techniques available, and we had this spark source machine which could measure them, but X-ray fluorescence machinery could not actually measure these things reliably. So we had a monopoly on niobium in depleted mid-ocean ridge basalts, and we exploited that, and so that's how we got these points here. So anyway, we noticed that when ratioed to uranium, they formed what looked like essentially a constant ratio, namely around, well, in detail, this was 47 plus or minus 10 or so, which contrasts strongly with estimates of the continental crust, which is the same thing you saw in the spidergrams on the last slide. And it's higher than the chondritic value. So here is something that you can perhaps use quantitatively. Now, this is a long time ago, and I had done a little bit at that time, but it's been more or less forgotten. And so I picked up, when you get older, you sort of try to remember, the smart things you did in your youth. So this is what I'm doing now. And I examined recent data sets. And I think they're stunning, actually. Not only that, they actually almost exactly confirm what we did then, which is total stroke of luck. Not, I think, I think it's almost a coincidence that, the current best average we get for mid-ocean ridge basalts is a niobium-uranium ratio of 46 rather than 47. Okay, so that we hit it lucky. I plotted this here against lanthanum ytterbium, just as a measure of the degree of of a partial melting. Something like the lanthanum-ytterbium ratio varies inversely with the degree of melting. At high degrees of melting, you get low lanthanum ytterbium ratios. At low melt fractions, you get high ratios, which tends to spread this thing out. This is not statistically the best way of showing that, and I've been taken to task for using this kind of plot, where something with a slope of 0 is what you're looking for. But it actually shows the relationship, I think, in an intuitive way better than the statistically better way, which I'll just flash in the following. The correct way of doing this to demonstrate the uniformity of such a ratio is to use log-log plots. And so there's log uranium versus log niobium, and there's log uranium versus log tantalum, which are very similar. And you see that here the slope is 0.976, and here the slope is log 1.032. So the ideal would be 1.00. So I use both of these pairs, niobium uranium and tantalum uranium, and I make the calculations. I bracket the results from these just to be on the safe side. Okay, so back to this here. You can see the niobium uranium does this pretty well. Niobium thorium, almost, not quite as good. Tantalum uranium, good. Many people use niobium lanthanum. I would warn against that. You see, this is not terribly constant. But let's push on. So this shows the same relationship I showed on this 1986 slide, namely the mid-ocean ridge basalts here. This is actually a different data set from, there are 3 data sets now with more, all of which give essentially the same answer with different amounts of scatter. There's the Gale and Langmuir data set, there's the Jenner and O'Neill data set, and there's the Arevalo and McDonough data set of mid-ocean ridge basalts. So there's lots and lots of good data, and all of them give you the same answer. And I show sometimes this one, sometimes another one. As the primitive mantle is distinctly lower, and then here are the average continental crust. Here's some arc averages of arc front volcanoes. And here are some subducting sediments, actually, individual arcs, okay? So all of that stuff is down here, and all of the oceanic stuff is up there. So now I want to know whether the ocean island basalts, where they fall, previously was just mid-ocean ridge basalts, but of course we also have these mantle plumes or whatever they are, ocean island basalts. And it's hard to use the uranium because the uranium is easily affected by alteration in an oxidizing atmosphere. So I plot thorium, which is not ideal, but it actually shows that that the niobium is part of the ocean island basalts, and the oceanic plateaus, for example, they're all part of the same population as mid-ocean ridge basalts. So they really belong together. Okay. Same equation that we had before, except instead of using epsilon neodymium now, I'm plugging in niobium uranium or tantalum uranium into this equation. Okay. Otherwise, it's exactly the same. Now we look what we get for results. Now, I plot this, the mass fraction of the residual mantle for niobium and tantalum uranium as a function of the uranium content of the continental crust. The major uncertainty here now is actually the estimate of the uranium content of the continental crust. And these different points are uranium concentrations of different authors. This is an outlier here now that not really taken terribly seriously anymore. This is Taylor and McLennan, 1985. McLennan and Taylor, a few years later, revised that to this point here. So I think most of the consensus uranium contents of the continental crust are between 1.1 and 1.3 ppm. Or for the average of the continental crust. So that's the bracket we're looking at. And here is for the niobium uranium ratio, and you see that you get about 0.6, mass fraction of 0.6 of the mantle to 0.8, depending on the uranium content. And for tantalum, you get the same, you get basically the same thing. this tantalum value is based on a different data set, which systematically has different tantalum data. It's not really clear why that's the case, but they also get different values for the tantalum standard. So that's an uncertainty that's of an analytical nature rather than a real nature. Okay, so 60 to 80% rather than 20 or 30% of the mantle is now the residual to the continental crust, if we make that calculation. And then if I calculate the concentration of all these elements, the whole spidergram, here are the old Salters and Strachey and Workman and Hart things in dotted lines, okay, way down depleted. And what I get now is this thing here. Much less depleted, much larger reservoir. Basically, the residual part of the mantle is now more diluted and therefore less depleted. Okay? Now, if we go back, so I had this paper all written with this result, and I was happy, and then I went back and said, well, wait a minute, what do I do with the epsilon now? How do I actually interpret the epsilon values? So I went back and I made the epsilon calculation. Then this is the one I showed you before for the Morb epsilon. I said, what kind of epsilon value would the residual reservoir have to have in order to have occupy 60 to 80% of the total mantle? Turn this around. So to get 60 to 80% here, and if that's the epsilon of 15, you need an epsilon value of 3, and this one is about 2, 60 to 80%, okay? So between here and 2. So that residual mantle would have to have an epsilon value of somewhere between 2 and 3 rather than 8.5. Or even if you include the mid-ocean, the ocean island basalts, they're somewhat lower, but they're not 2. So there's a real. So if I plot the mid-ocean ridge basalts have epsilon 8.5 here, I plotted. This is not a very statistically terribly sound way of doing this. It's hard to actually know what the average value should be, but you can make a guess here. What I got was 4.5, plus or minus 2 or something. The point is we don't have a residual mantle with an epsilon value of 2 or 3 here. Almost all of these things are higher. So there's a real dilemma here. The mantle doesn't show in neodymium isotopes what it should be if the residual reservoir is really 60 to 80% of the total mantle. So how do we resolve that? So I think this is a fundamental contradiction. The isotopic, I just repeat what I just said to let it sink in, okay? The isotopic mass balance yields a small, highly depleted mantle residue. The niobium uranium mass balance yields a large but much less depleted reservoir. This large residual mantle reservoir cannot be reconciled with the high degree of depletion indicated by the neodymium isotopes. I have found no way of bringing these two things together. What do? We go back to Maud Boyer and Rick Carlson's papers, who postulated an early enriched and early depleted mantle reservoir on the basis of something totally different a little over 10 years ago. And they have almost revoked this by now, if I'm not mistaken. Not quite, but the neodymium, I'm not going to get into the neodymium-142, don't worry. But the rationale here is really is totally different. It's not dependent on a balance of a short-lived isotopes, but simply on this discrepancy, what we get from two different parameters for the same physical quantities. So I can resolve this problem quite easily by segregating a now hidden or possibly lost early enriched reservoir, similar to Boyer and Carlson's early enriched reservoir. Okay? So the mantle now that we're differentiating doesn't start from epsilon equal to 0, but it starts from epsilon equal to, let's say, 3. So in order to get to the Morb reservoir, we only have to go up 5 units, not 8. Okay, it's actually pretty simple. And also, I find really no real escape from that. Now, to model this quantitatively, maybe one can actually constrain this well, but I haven't found a way. There are so many more or less free parameters. I've decided to just give you one example that works, okay? But there may be others that are similar, but I find it difficult to put bounds on it. At least I haven't done it. So the example I have chosen is this. I'm melting the primordial mantle, big impact, total magma ocean, make a 10% melt of that, which would give you sort of a mid-ocean ridge-like basaltic melt. And then I take, so I don't bury all that 10% melt. I don't segregate all that, but I only take a small fraction of that, namely 3%. That's my small f of 3. So 3% of such a mantle is now either lost or permanently hidden in the lowermost mantle, LLSVP, maybe, okay? So that's my example. Melt fraction, 10%, segregated fraction, 3%. And then what do we get? I calculate the compositions from that. That early melt, and using somebody's partition coefficient. I think this is Workman and Hart's partition coefficient. Every time you make a calculation, you have to make up your mind what kind of partition coefficients you use. So and then you get a different answer. It's, as I said, I'll give you an example. So the most highly incompatible elements are enriched by a factor of 10. When your melt fraction is 10%, that stands to reason, and it goes down a little bit. And the depleted reservoir is slightly depleted. So that early depleted reservoir then has something like 0.75 or so, or 7.2, I think. So that's what the depleted reservoir looks like. It doesn't look that different from 1, but it makes quite a difference for the epsilon value. And I see Rick is nodding because he's done that same thing many times. Okay. So if I do that, and I now take the early depleted reservoir uranium of 0.725 from that previous plot, then everything shifts. My previous calculation, I have a different starting point for my mass balance calculation, and these things shift up even higher. Namely, they very quickly go through 100% of depleted mantle, and you can see that if that's that green line here. Okay, so Rudnick and Gau's uranium concentration of 1.3 ppm in the continental crust is already out of bounds because it would require more than 100% a depleted reservoir. But the Taylor and McLennan of 1.1 is very close, actually, to essentially the total mantle being residual now to that new continental crust. So that's basically where I am now. Essentially, the whole mantle looks like is depleted after that early depletion event generated by the segregation of that early enriched reservoir. So I try to depict that again here, the two-stage process. The primitive mantle is up here. The early segregation of the early depleted, the early enriched thing makes that brown line, slight depletion, and then extracting the continental crust gets us down to these things. And this one, I made it in a dashed way because it's already, it's actually not correct anymore because the uranium content of that continental crust is too high. but you see roughly that the thorium and uranium content of these things are now about 0.4, 40% of the primitive value. So they're still much less depleted than the workman and hard thorium and uranium, which are very, very severely depleted. And that is essentially where I am. If someone has a better idea of how you can reconcile these things, I'd like to find out about it. I have not been able to actually think of another solution that avoids segregating this early enriched reservoir and creating an early depletion event. That's at least in any way simple. So to look at the continental crust a little bit, I wanted to know what is the average age of the continental crust. There's a huge literature on that. And most of the current papers are actually interested in, how was the continental crust 4 billion years, and if so, how much, and so forth. But for the mass balance calculation, that's not relevant. What's relevant for the mass balance calculation is what is the age of the currently preserved continental crust. That's what we're looking at. We're looking now. We're not looking 4 billion years ago. So this is, I've taken this from a paper by Rosas and Koranaga, and this would be something like half of that crust would be about 2.2 or 2.3 billion years old. And that fits reasonably well with the field evidence. I won't go into that. And just to sort of show you an evolution diagram of what that looks like, you have 4.5 billion years ago, you generate this early depleted reservoir, which then has a growth rate of the epsilon neodymium. And if you then extract all at one time, of course, this is not realistic, but it's good enough for the mass balance. The continental crust, you end up with a mantle that's somewhere between the present-day mid-ocean ridge basalts and the present-day ocean island basalts. And so that puts you in the right ballpark. As they say in this country, we don't use that expression in Germany. I think that's where, no, wait a minute. That's it, okay. And just to remind you, I think now geologically, geophysically, this is not as outlandish as it once seemed to be. I think there's geophysics, the deep mantle geophysics is deeply concerned with what the nature of these LLSVPs, and that might well be the location of such a reservoir. And I'll list you some conclusions here. I'll still have a couple of minutes, so we can go through them. The mantle was initially depleted by extraction isolation of a small early enriched reservoir. Subsequent segregation of continental crust caused additional depletion. So it's like a two-stage depletion that we need in order to reconcile the results from these two parameters. The total extent of depletion is far less extreme than previously thought. The uranium and thorium contents of that depleted reservoir are only about 0.4 times the primitive mantle values, not 0.1. Both the mid-ocean ridge and the ocean island basalt sources are residual and complementary to the continental crust. Corollary of that is that ocean island basalt sources are not from the primitive mantle. And the age of the early enriched reservoir formation is not well constrained, unlike the Borden and Carlson one, which was very constrained because of the short-lived isotopes. Here, the short-lived isotopes don't enter into it. Except the only constraint we have is that it must precede the extraction of significant continental crust, at least continental crust that exists now. And those are the bullet points that you can take home with you. And I think I am at the end. Yes. Thank you very much. This is a cartoon of Holden and Vogt. Back the older ones amongst us remember these wonderful cartoons that these guys made in the 1977 EOS issues about plate tectonics and mantle plumes and so forth, making fun of everybody. And this is a newer version, I think. I think you will find that in the mantleplumes.org website. That they have revived some of these cartoons. Okay, thanks very much.
Thanks for the wonderful talk. As a mantle geochemist, I think my temptation would be to call this difference between the extent of depletion of the depleted mantle from the neodymium isotopes versus niobium uranium, maybe the niobium paradox. Would you be okay with that?
Well, I'd call it the neodymium paradox.
That's not reserved for 142? Okay, the neodymium-niobium paradox. I was wondering about another possible solution to it, which I don't know if you've considered, which is that there is an enriched reservoir sitting in the mantle, which is recycled oceanic crust, which doesn't have fractionated niobium uranium, but does have fractionated samarium neodymium.
That's basically what I'm talking about.
Mm-hmm. So perhaps, would that be a solution to this, that basically it's just not necessarily maybe a magma ocean related process, but just the continuous process and generation of oceanic crust and subduction and sequestration of oceanic crust in the mantle to some extent over Earth history that's produced this difference?
That's tempting to think that way, and I think it comes close. I think it's basically something like oceanic crust, because as you point out, the property of this reservoir is not to behave like continental crust. In other words, it doesn't touch the niobium-uranium ratio, but it does touch the samarium-neodymium ratio and all the other parent-daughter ratios. So that's exactly what an oceanic crust would do. The only problem is if it's like part of a continuous segregation and storage with recycling back, it would have to be shown, and I have to admit I haven't made that effort, it would have to be shown that this can actually be sufficiently radiogenic. In other words, you need to store some of that stuff for a much longer time than what we see. The really low epsilon neodymium ocean island basalts that we do find, namely Pitcairn and a few of these goodies that we all love, they show very clear signs of some recycled continental material, and so they cannot be abused for that purpose. So to have things that have normal niobium-uranium ratios, they tend to have epsilon values, of greater than +3. Okay. So I think unless there is it could be a continuous process. Okay. And at some point, if there are sufficiently large differences in the rates of recycling of things that go deep and things that don't go so deep and so forth, one can think of mechanisms. You can model these with a two-stage model, where one thing happens at the beginning and the rest happens later on. We've all done that, but I don't think we can get away from having a lot of that stuff stored quite early on and not reappearing. I don't know any ocean island basalts that we're getting that have these really low epsilon values that are not derived from some kind of recycled continental material. That's my difficulty.
A couple of questions. First of all, going back to your spidergrams, you have anomalies in lead, and I think it was also titanium. If you play the same game, do they give you the same answer as the uranium niobium?
I have not played the game for titanium. In principle, you might. The reason why I stayed away from titanium is that the titanium, I think, is too easily fractionated by sort of late magmatic processes. So I don't trust it. Or you would have to make sure that you're always dealing with primitive magmas which haven't suffered, so that those titanium values don't reflect sources. For lead, I have actually done, in this 1986 paper, I actually made the rough calculation for lead, and it's similar as for the niobium. It's just that the quality of the lead data tend to be not as good as the niobium. And also the lead can be compromised, especially in mid-ocean-rich basalts, by fractionation effects due to plagioclase. And so as plagioclase precipitates, it takes out europium, it takes out strontium, and it takes out some of the lead. And once that happens, you don't want to use lead anymore, okay? So niobium is the most robust of those, as well as tantalum.
So my second question is, if the mantle is less depleted than we thought, quite significantly less depleted, does that mean we've been getting our calculations of partial melting at mid-ocean ridges wrong?
If you're using the classic depleted mantle, the answer is yes, I think. If you look at the paper of Workman and Hart, they actually modeled, they made this test, supposedly. They took their mantle, their highly depleted mantle, and they did a partial melting model to extract normal morb. And they got a melt fraction of 6%, as I can recall. Now, they actually cheated a bit because I don't want to go into detail. I've redone that calculation. I get something closer to 3%. Now, you're not going to tell me that we're making mid-ocean-rich basalts, on average by 3% melting. If you take that less depleted mantle, you can do it by 10, 12% melting, which is, more acceptable, actually.
My follow-up is your number more consistent with the geophysics than the older number?
With what geophysics?
Well, there are estimates, I think, based on rates at which mantle is, or first of all, on seismic profiles below mid-ocean ridges, and also on various other elevation and things like that, about how much material is coming up and spreading in different places. But there are people in the audience who know much more about that than I do.
I don't actually know what specific parameter I would be needing to look at to answer that question.
It was my impression that there were estimates based on geophysics for the degree of partial melting, but
No, it's all experimental petrology, and yeah. Mike can answer that. I'll point out too that the Workman and Hart trace element pattern for the depleted mantle is based on, also Salters and Straka, is based on an assumed assumed history of extraction of the continental crust, because it's based there are a couple steps in that require reliance on the isotopes. So it basically is a little bit of a circular model, is that if the continental crustal extraction didn't occur in the model that they assumed, then you're not going to get that result. So if you assume a different history of continental extraction, you get a different trace element pattern from the depleted mantle, even in the simple two component mass balance.
Yeah, particularly for the timing of the continental extraction. Yeah.
Yeah, forgive me if I missed this, but how well do we know the niobium content of the middle and lower crust? And would that, I saw that you're taking different crustal estimates into the uranium content, but the niobium-uranium ratio of the crust and with age, I mean, if you're extracting continental crust by a different mechanism in the Archean, for instance, how would that play into the outputs that you're getting here?
Yeah, you will see actually, I haven't paid too much attention to that. I have taken what different authors have guessed and the scatter on my line, the different data points. They're just different people's estimates, not only of the uranium content, which gives you the abscissa, but also some scatter vertically. That's the niobium-uranium ratio, which differs slightly in different people's crust, and it shows you that it doesn't actually matter all that much. It's not the calculation is not terribly sensitive to that. It's much more sensitive to the absolute uranium content of the continental crust, and that's the major uncertainty, actually. It's just the way it works out. What is more serious, actually, which I haven't mentioned, is that when I first made these calculations, I used the chondritic niobium-uranium ratio for the Earth, which is in McDonough and Son's paper 32.4, I think. And then I realized, and I was getting different things for niobium-uranium and for tantalum-uranium ratio. Then I looked more carefully at something that geochemists tend to know is namely the niobium-tantalum ratio of the Earth is not chondritic. So there's a problem there. So whether there's niobium in the core, which seems the most likely version right now, or not, it's pretty clear that the bulk Earth does not have a chondritic niobium-tantalum ratio, but is low by 10–15%. And so it was not until I actually made an adjustment for that using niobium-tantalum ratio to lower the niobium-uranium ratio of the bulk Earth composition from that given by McDonough and Son from 32 to 27 point something, okay, and then actually magically I got quite concordant answers for the tantalum and the niobium calculation. So that became internally consistent. Again, I think whatever you use for niobium and tantalum in the crust tends to be demagnified in that calculation.
Hi, Al, over here. Thank you very much for the talk. And you and I and others in this audience have been attending geochemical talks of this sort for a long time. You're trying to resolve a very, very complicated three-dimensional spatial and also temporal problem about Earth. And the thing that strikes me is that we're still using XY plots, maybe a ratio against a ratio, or looking at one element, looking at a second element. But these days, we have 30, 40 trace elements. We have dozens of isotopic ratios. Has anybody been trying to use all of the data simultaneously instead of throwing out 99% of what we know and focusing on a single element at a time? It's almost like trying to use a scalar to define a four-dimensional problem. And the approaches of using data analytics allows you to use all the data simultaneously to get a much richer picture. I'm just wondering, have you thought about that? Has anybody been thinking about that other than just using XY plots?
I have often thought about that. And every time I think about it, I reject it. I think in a way, the niobium epsilon neodymium discrepancy shows why you probably don't want to do that. Because if you throw everything into one pot and try to get an optimum solution, but the different, the different parameters that go into that mixing bowl actually measure qualitatively different things, you're not going to clarify things. You're going to confuse things. So I think looking at the effect of what one parameter does at a time before you do these things together is still the best strategy. And it's also it's devilishly hard. That the quality of there's a whole issue of data quality and big differences in thinking about using the big data and throwing all of them into one pot, and those saying, well, you want to use the most precise data and so forth and so on. So there are many issues involved here, but mostly I think is that if the kind of processes that your different parameters respond to are qualitatively different, I don't see that you really, that this is the best way forward to sort these things out rather than looking at them one by one.
Yeah, I would just.
I know multivariate analysis supposedly solves all that, but
multiple processes,
yeah.
using multiple parameters
Yeah.
is the way to solve it.
Yeah. It's not my taste.
I'd like to ask you what you think currently about the primitive mantle debate, right?
Where are you
think-
sitting? Oh, there. Okay. I hear the sound.
It comes from everywhere. Yeah. The thing that I think still strikes me about your talk, which you didn't emphasize a whole lot, but touched on a little bit, is the fact that there does not appear to be so much isotopic evidence for the existence of primitive mantle. In other words, if you restrict yourself to all of those samples that have primitive mantle-like neodymium isotopes, hafnium isotopes, for example, then they look non-primitive in other ways. And so I'm wondering if you still subscribe to that notion, or what you think about the current volume of primitive mantle in the present day mantle.
I'm not sure let me try to rephrase and you tell me whether I understood your question correctly, okay? In the isotope diagrams, there is always a point that represents the primitive mantle. And there has been a tendency when you find samples that fall on that point, it says, well, maybe that is actually derived from primitive mantle. And the alternative is that if your data array happens to go through that primitive mantle point, but crosses it, there's two ways of getting a seemingly primitive mantle point, namely one of actually having primitive mantle, the other one is just mixing things from both ends of that, and you will have some samples which look primitive, but they're actually mixtures of differentiated things. And this discussion permeates the mantle xenolith literature. It permeates the isotopic basalt literature, and I have convinced myself, at least to the extent that there are parameters like niobium uranium in these samples that are distinctly non-primitive, is that these are back mixtures. They do not represent primitive material. Was that the sense of your question? Yeah.
That's half the question. So do you think that there is no primitive mantle left?
I think if there is, it's very little, because I mean that's once I adjust the calculation, there's very little room for that. I mean, there might be smidgens of it, but I don't think we see it.
Last couple questions. So I remember, Al, a comment you made a long time ago at another talk. Where you said, after the mag motion separates and we have deep processes related to the mag motion phase, we're not going to have any primitive mantle. Something has to separate from something else mineralogically. And I don't know if you remember saying this, but I remember it very well. I was a young student. And it stuck with me because in the debate we have now for these long-lived radio tracers that have really short half-lives, like 9 million years, those are preserved. And if they're preserved, I totally agree with you. You must have almost no primitive mantle
it must be a very small reservoir, or we just don't have any left. And I think everything we see are mixing diagrams between things like what was done for osmium, for example, where mantle xenoliths from a subcontinental mantle were mixed towards a line that happened to go through a primitive mantle, projecting a point that's just simply a depletion projection.
Yeah, I agree with you.
Last question.
So if there's no primitive mantle, how do you explain the primitive helium and neon coming out of the Earth?
I think there are in these early differentiated, whatever they are, okay, early enriched reservoir. I think there may well be, the pockets of where that stuff is residing, where the primordial xenon, neon, and helium is residing, and I think it leaks. It leaks from those things into the main silicate part of what we see in mantle plumes. So I think that the bulk of the material that we sample by plumes is not certainly not from the early enriched material, but just from the general, run-of-the-mill, from the depleted thing. But the early enriched reservoir or reservoirs or whatever are the home of these noble gases, and they will leak out.
Can you really trap primitive noble gases in an early crust or something that's extracted crust?
Well, I think it's very evident that we must, because otherwise, if you couldn't trap them, we wouldn't have them anymore. I'm sorry.
Al's around. He's got a pretty full schedule today. He's around till end of next week, almost the end of next week. Is that right?
I think we leave on Friday.
Yeah. So you get plenty of time to talk with him, but
Yeah.
I encourage you to do so. I don't think we've solved this problem yet, but it's getting very interesting. So thanks again, Al.
Thank you.
Great job. I like it.
So, okay. I'm going to switch this off.
Switch you off. Yeah, other side.
On the screen, it was hard to get anything done.
Nice summary, though.